This is MA359 Assignment 1, Question 1. So it asks us to find an increasing sequence F1, F2, so on, of sigma-algebras whose union is not a sigma-algebra. So the hint says it's easier than you might think. So you might originally say x equals easier than you might think is a right answer, but it turns out this is not the correct answer, unfortunately. So this is not the right line of reasoning to follow. So you can discard the hint for this question, and one way you could do this, in fact, any increasing sequence of sigma-algebra you choose, their union would not be a sigma-algebra, so you could literally choose anything. But an easy example would be f of n being sigma-algebra generated by 1, 2, up to n. So what would that look like? Well, it would look like every subset of it, right? So basically this is just the power set of 1, 2, up to n. Sorry, the sigma-algebra generated by these singletons, like this, right? So we're taking these single elements and we're generating the sigma-algebra out of them by taking unions, intersections, and so on. And this it's pretty easy to show that this would give you this, right? Because we can just take the intersection to get the empty set and the unions of any amount of these to get any element in the power set. So these two are equal. Okay, and so what we notice is that every element in this f sub n is finite, right? Because we're taking the power set of a finite set, and any subset of a finite set will be finite. So elements in Fn are finite. Okay, this is important. So that's important. That's kind of like a lemma. So now we want to consider this big F as the union of these Fn's. And we want to show it's not a sigma-algebra. So we're going to do this by contradiction. So suppose F is a sigma-algebra. Okay, so what does that mean? Well, it satisfies all the rules a sigma-algebra has to, like complements, and in particular it satisfies the countable union property. So if we have any elements in here, then we can take a countable union of them and it will still be in it. It will be closed under countable unions. So what elements are in this union? Well, we know that the singleton containing 1 is in it. We know that singleton containing 2 is in it, because, F2 is in it. And the singleton containing 3 is in it, because F3 is in it, right? We know this is in it. And all the way for every single n. So for every n, we have it. Because we're taking the union of all the n's, we have it for every single n. And so what we can do is we can take the union of all of them, right? So we can just the union over the n's of these singletons, like this. And this would give you the natural numbers, right? Because we're taking the union over the natural numbers of the n, and then that would just give you every single n as one set, the natural numbers. And so we see that the natural numbers, this is in this f, so natural numbers is in f. So this gives us contradiction. So why does it give us contradiction? Well, contradiction because natural numbers is infinite, right? Elements in f of n are finite, and because we're taking the union of elements in f of n, any element in this f will be an element in one of these f of n's, and so it's finite. So I should have said that elements in f are finite. This is double star, let's say, and contradiction by double star. So that's it. That's assignment 1, question 1. Thanks for watching.